Hello. So this is all about internal resistance. It's a part of the AS Physics Syllabus in topic 12, practical circuits. So internal resistance, as the name suggests, is basically the resistance inside the supply of voltage. And what that means is if you have a pretty basic circuit where you have a cell and then you probably have like something here like a lamp. What supplies the voltage here is obviously the cell. And imagine if, other than this very obvious resistance right here, you also had a very, very small resistance of the battery itself. That means that if you had a battery and it says, okay, this is a 3-volt battery, then actually a little bit of the 3 volts is going to be used within the battery because there's a resistance inside it. And therefore, if you were to connect like a voltmeter to like kind of measure the voltage outside of this power supply, it would not be the same as what's given here, what it says it's going to supply. It would not be the same because what's being measured here is measuring those like charges and their electric potential energies that already came out of the battery, but they already used some of the volt inside the battery. So it doesn't only have to be a battery or a cell, it could also be a power supply in which the circuit might look a little bit like this. In any case, there's always the fact that there's going to be a bit of resistance within these like suppliers of voltages. So it results in the EMF or the voltage provided by supply not equaling the voltage across its terminals. So the power supply, which is like this, if this was used to basically supply your voltage, there might be some resistance in the wires or the components of the power supply. If you were using a battery, just like here, in order to provide voltage, then maybe there would be resistance in the acid or the chemicals within the battery. And that's where internal resistance basically stems from. So the voltage across its terminals and also the internal resistance will depend on what is in the external circuit. And we're going to talk more about that later. So some electrical potential energy of charges are transformed into internal energy as they do work against internal resistance of the cell, and as a result the battery heats up. So what this means is if you had like, let's say this is kind of the insides of a battery, and then you had like some acid in here, and then there was an electron that was going through it. Now the battery will supply it, let's say 3 volts. But as it moves along and then it goes outside, there's a little bit of resistance that's hindering its motion that it has to overcome. So it does a bit of work against it in order to actually push itself out of there. And that's what they mean by they do work against internal resistance. As they do this, the sort of electrical energy that they had, which was 3 volts, is going to be transformed into internal energy. Internal energy is just another word for heat energy, which means that they're going to produce heat. They're going to let the energy go as heat. So when you connect a battery, maybe you have a toy or a lamp, you might realize that the battery becomes hotter as you turn it on, and that's exactly the reason why. It's because these electrons are using a bit of their energy within the cell in order to overcome the resisting forces or the internal resistance of the cell, and therefore it will heat up. So we can represent it like this right here, where basically if this whole thing was the battery, and just picture right here that this is actually a battery, and we've kind of like divided it into the cell part and then the resistance part. And it's basically just, it has two functions. A part of it is to supply voltage. A part of it is also resistance, as we have seen before, maybe within the acid. And what we've actually just done is like pretended that they were two components so that we could take a look at them clearer. But actually they're within a component. And that's why we have these dotted lines right here, which indicate that this is actually just one component. So the small r is the internal resistance, the resistance within the battery, and it's usually going to be denoted as this in most situations. The big R right here is basically the external resistance, whatever resistance you see in the external circuit. And this is just the current that's moving in and about, just like conventional current from positive to negative. So what we can see here is that this external resistance and the internal resistance are in series, which means the total resistance, total R, is going to equal the external resistance plus the internal resistance because they are in a series. And so, yeah, you might have heard of the equation V equals IR. Well, if we look at the big picture of the entire circuit, the electromotive force will actually be denoted as E, which is basically that the electromotive force that's going to every single part of the cell, not only for this one resistance. So using V equals IR, E is basically I times total resistance. The difference between voltage and e.m.f is that voltage might only refer to 2 points in a cell, maybe like between these 2 points in a cell, maybe. I can put a V there. But an e.m.f, which is electromotive force, or it's denoted by E here, is basically the potential difference between the whole cell, between these two parts of it. And it's basically not just the kind of energy used when you go through this part, it's the energy supplied to an electron as it moves, or a charge as it moves all throughout the entire circuit. So we have to put into perspective the internal resistance as well, and that's the difference, while voltage doesn't always do that. So we can get the fact that, R plus R is the total resistance, so if we times that by the current, then we're going to get electromotive force. Since V equals IR, let's say this is the voltage across this external resistance, we also get the fact that, if we decided to substitute these two equations together, you would get voltage equals E minus IR. Because if we, multiplied it together, IR plus IR, this will become V. So, yeah, and then we get the equation if we send this one over right here. So since we get this final equation, which is just a derivative of these two things, it's not very much of its own equation in any way. We can tell that the terminal potential difference, or the terminal kind of might be the one here, I guess. That equals the e.m.f, which is the original electromotive force, minus the lost volts, which was IR, which is basically the volts that were used to overcome the internal resistance. So if we put a V over here, we put a voltmeter over here, then we would see that, we would get IR, which is basically lost volts. So this is pretty important. Terminal PD equals e.m.f minus lost volts. The potential difference across internal resistance cell is called lost volts, which is basically what I've drawn here. So this is the definition for lost volts, the potential difference across internal resistance. So according to the equations that we've made here, if there is a high current, then that means that, for the same value of internal resistance, the entire IR, because IR will go up, which means that lost volts will become higher. So the higher the current you have, the lower the terminal PD it's going to be, because this is going to be bigger. Therefore, if you short circuit a circuit, which means that you basically leave nothing outside of the circuit, if you short circuit it, it would look something like this. There's nothing outside it, no resistance. It will make R really low, like the only R that would be is the minuscule amount of resistance within the actual wire, which is very, very low, especially if you're using like copper wire. And that means that I will just shoot up in proportion because, V equals IR. So therefore, IR will also go up, the lost volts will also go up, and Therefore, the energy lost as heat will become too high. It may also damage the power supply by setting it on fire or melting it. So when current is maximized, and this is another way for saying that the circuit has been short-circuited, then we say that R becomes very close to zero when you short-circuit a circuit. And therefore, because E used to be IR plus I small r, this becomes very close to zero, and therefore we have electromotive force equals the lost volts. And as R reaches infinity, so when the resistor outside of the circuit, so in the external circuit, if this becomes extremely high to the point where it reaches infinity, then the terminal voltage will be very close to the electromotive force. And why is that? It's because if this becomes extremely high, then current will become extremely low. And so if we have E is IR plus lost volts, as I becomes very low, and this becomes very high, but this stays the same, this will be extremely close to zero. For example, if the current was 0.0000001, that will be extremely close to zero. And therefore, E equals IR means that the terminal voltage, which is basically over here, that's IR, kind of measuring the R right here, this will become very close to the electromotive force. So the more current a battery supplies, the higher the lost volts and the lower the terminal voltage. And that's about it for internal resistance. Thank you.